So here are the topics of today's lecture. So today I will first discuss about strain measurement, how to measure strain in real life. Okay, so we'll discuss about strain gauge and strain rosette, which can be used for measuring strain. And second topic we're gonna discuss is Mohr circle in 3D for strain analysis, which will be similar to what we have learned for Mohr circle for stress problem. As a third topic, we'll briefly discuss about the relationship between Mohr circle for stress and Mohr circle for strain, and we'll also discuss about if the principal axis obtained from stress analysis is the same as the stress principal axis obtained from strain analysis. As a last topic, we'll solve a few example problems. So let's begin from the first one, strain measurement. Let me first introduce what strain gauge is. So some of you already know about the concept of strain gauge, or some of you may not. But let me give you a simplified geometry of strain gauge. Strain gauge is a sort of like a electrical wiring that can be attached on the surface of mechanical component and mechanical devices. So if you attach a these kind of material, like a thin material where you have quite long electrical path like this, and suppose that under thermal expansion or under mechanical strain, this entire structure would expand. Okay, so what you can expect is, along that direction, the wire would elongate it too, and because you have longer electrical paths, the resistance would increases, right? So you can connect, voltage and try to measure the voltage here and resistance here, and by measuring the current, you can measure the resistance. Okay, and what you can do is, as a function of a strain, you can obtain the curve of the change of resistance. Okay, of course resistance would increase over strain, and out of this calibration curve you can predict the strain after making this calibration curve. And if you move this to other surface, and suppose then you measure measure the strain here, you measure the resistance here, then your strain estimation is here. Okay, that's the principle of strain measurement along one direction. Of course you can expect change of strain in the other direction, but when you change the the material in the other direction, you only expect the increase of the electrical path along these small sections, and this kind of change would not affect the resistance too much. Only if you have mechanical strain along this long direction, you can expect significant change in electrical path and expect the significant change in resistance. Okay, so out of this strain gauge, you can realize that, okay, at least for normal strain I can measure, but if somebody asks you how can we measure shear strain, it's quite hard to answer. Like, it's not easy to devise a device where you can directly measure shear strain. So here, our answer, and one of the common methods to measure shear strain is the usage of so-called StrainRosette. So StrainRosette is a device composed of 3 strain gauges. So that looks like this. Each strain gauge has like a same origin. If you extend this direction and long direction here and long direction here, they meet at exactly 1 point. Okay, so after having 3 strain gauges that are aligned on the same origin point, and here what you do is you measure normal strain along 3 direction: x direction, y direction, and this b direction. Okay, and suppose that for the simplicity, and this is 45 degree, then you're gonna get like a even simpler equation set. So here what I want to notice is that the equation we have in previous class, if we have xy coordinate like this, if you have also x prime, y prime like this, okay, and suppose that you are representing same strain state with respect to different coordinate system, xy coordinate system or x prime y prime coordinate system, then what you learned is that epsilon x prime is the same as the expression in terms of ex, ey, and cosine theta and sine theta. Yeah, this is theta and gamma xy. Okay, so you can represent strain component along x prime direction using strain component, normal strain along x, normal strain along y, and shear strain along xy direction. Okay, so when theta is 45 degree, and then if you plug in the number, yeah, this one will be gone, and you only have sine 2 theta is 1, so you have gamma over 2 here. You have the first term as it is, and this epsilon x prime is same as epsilon OB in our figure on the left, and what you found is the relationship between epsilon OB, which is normal strain, epsilon x, which is horizontal normal strain, epsilon y, which is vertical normal strain, and unknown, yeah, gamma xy. This is unknown. However, we measure information. We already have the information for 3 normal strain. We can represent gamma xy in terms of epsilon OB, epsilon x, and epsilon y. This is how you measure the shear strain out of 3 normal strain measurement. Okay, so instead of using 45 degree, what you can do is you can place strain gauge along arbitrary 3 distinct directions. Then you can, based on linear algebra, you can obtain the shear strain. Okay, so from the previous lecture note, maybe this page can be wrong. So what you can derive is that epsilon x prime can be written as epsilon x cosine something, epsilon y sine something, and gamma xy sine theta and cosine theta. So what you can do here is suppose that instead of x, y, and this 45 degree, you can orient normal strain strain gauge along theta 1 direction, theta 2 direction, and theta 3 direction. And what you can do is you can write down epsilon 1, epsilon 2, epsilon 3, which is the normal strain along theta 1, theta 2, and theta 3 in terms of epsilon, gamma, epsilon y, and theta. Here we already know theta 1, theta 2, and theta 3. 3 unknowns are epsilon x, epsilon y, and gamma xy. So out of these 3 distinct arbitrary strain direction measurement, you can obtain epsilon x, epsilon y, and gamma xy. Okay. Yeah. Of course, here what you have to notice is that epsilon 1 should be different from epsilon 2, epsilon 1 should be different from epsilon 3, epsilon 1 and epsilon 2, they must be different, so that you want to have 3 linearly independent equation, right? So if you have 3 linearly independent equation, and if you have 3 unknown, epsilon x, epsilon y, gamma xy, you can always find the answers for epsilon x, epsilon y, and gamma xy. Okay, of course, out of these, the most simpler method is these 3 arrangement, x, y, and 45 degree. Okay, this will have smallest error in the presence of the measurement error. And why is that? Regarding that, you may refer the answer out of the linear algebra later, but here, just to, that will be beyond the scope of this course. Please be satisfied with that. If you have 3 distinct directions where you can have 3 linearly independent relationship regarding epsilon 1, epsilon 2, epsilon 3, then you can obtain 3 unknowns, which of course is from the characteristic of linear equations. Okay, so this is a so-called StrainRosette, and out of 3 normal strain direction strain measurement, you can obtain shear strain and characterize epsilon x, epsilon y, and gamma xy. Okay, and out of this measurement, you can construct more circle and do strain analysis. And out of strain analysis and strain transformation, you can determine whether the structure is reliable or not. That's the typical flows of Me to Threon. So yeah, with this, let me finish the recording, the first video lecture here. Okay.